Hello everyone, I'm Jeroen.
And I'm Jelle.
And we are students at the University of Twente at the Integrated Circuit Design Group. We'd like to talk to you today about successive approximation register analog to digital converters, or SAR ADCs for short. To do this, we'll first discuss why we need such a converter. We will treat the language of the computer. Then we will use a physical analogy to explain the concept of SAR ADCs, after which we will perform a conversion with this analogy. Next, we will map the components of this analogy, this physical analogy, onto the circuit, and then we will go through a conversion cycle with the actual circuit. And finally, we will end with an example of a real-world application of such a SAR ADC. So why do we need an analog to digital converter? Imagine an example where a human tries to communicate with a computer, specifically a phone. The human talks, but the phone does not understand what the human is saying because it does not speak the language of humans. The computer tries to respond in its own language, binary. However, typically, humans do not understand this. To facilitate this communication between human and phone, we require two translators, one for each direction. The analog to digital converter, ADC for short, converts the analog human language into binary. And the digital to analog converter, DAC for short, translates the binary computer language to the analog human language. Now, the computer can use the ADC to understand what the human says when they speak, and similarly, the computer can use the DAC to allow the human to understand it. In this video, we will focus on the ADC. There are many cases where such an ADC is needed. For example, when a human speaks to a computer, wants to enter data into a computer, or wants to read out sensor data, such as from one of these sensors.
Hello, this is Jelle. Jeroen has just explained why we need ADCs. But before we can discuss the workings of ADCs, I will first need to explain the computer language, binary. To do this, we will use a lamp analogy. The lamp is off when the switch is open, which represents the off or zero state. When the switch is closed, the lamp will light, representing the on or 1 state. So now we have two states, on and off, 1 and 0. We now know that what binary means, on or off, only two possible states. I will now explain how counting is performed in binary. To do this, I will again use lamps. Let's imagine we have a 1 watt lamp, which can be either off or on, thus having two possible states. If we want to produce 2 watts of power, we could add a second 1 watt lamp, but this would not allow production of 3 watts. If we instead add a 2 watt lamp, we can produce 0, 1, 2 or 3 watts, depending on which lamp we can turn on. Let's show this. The 2 watt lamp can be off or on. The 1 watt lamp can also be off or on. This gives us a maximum power of 3 watts and 4 unique states. If we want to increase the power to 4 watts, we can add a 1, 2 or 3 watt lamp. However, it is better to add a 4 watt lamp. This allows us to both generate 7 watts and have 8 unique states, among which is a 4 watt state. This 4 watt lamp can again be off or on. And the 2 and 1 watt lamps can also again be off or on, giving 8 unique states, 2 times as many as before. This concept can be extended to any arbitrary number of increasingly powerful lamps. It should be clear by now that any time a doubly large lamp is added, the number of unique states increases by a factor of 2. I have explained how the binary system can be used to make large numbers of unique states. Now a formalized mathematical method will be given, allowing us to find the decimal representation of an arbitrary binary number. In the decimal system we have available to us 10 digits, 0 to 9. Let us take an arbitrary decimal number and dissect it to reveal its structure. The number 528 will be used to illustrate how a number is constructed in the decimal system. The number can be represented as 5 hundreds, 2 tens and 8 ones, which can be rewritten into multiples of powers of 10. Powers of 10 are used because there are 10 digits in the decimal system. The components can be added together again, producing the original number, 528. Now we will have a look at the binary system. We will draw parallels to the decimal system to learn how to translate binary into decimal. The binary system only has 2 digits, as previously mentioned. Let us again take an arbitrary valid number. This number is also dissected into 3 different parts. Because only 2 digits are available in the binary system, powers of 2 are used. Each leftward digit will increase in weight by a factor of 2. unlike in the decimal system, where each leftward digit increases in weight by a factor of 10. With this knowledge, we can rewrite the components of this binary number in decimal form. And the result, we find that 101 is the binary equivalent of the decimal number 5. I have shown how to convert binary numbers to decimal numbers. Now we can proceed with the explanation of the SAR algorithm. To explain the SAR algorithm, we will use a balance scale. On the right-hand side of the balance, we will place an unknown weight, for which we will try to find the digital approximation. To achieve this, we will attempt to balance the scale as well as possible by placing known weights on the left-hand side of the balance. The scale readout is negative when the left-hand side of the balance is heavier, positive when the right-hand side is heavier, and 0 when the scale is perfectly balanced. The graph shows this readout of the scale balance versus time. The 5 binary digits shown at the bottom of the screen represent the weights added so far. To the leftmost digit represents 16 units of weight, with each consecutive weight to the right being twice as light. The unknown weight is added to the right-hand side of the scale. The value of the weight is shown, but we will proceed as if it is unknown, as would be the case in a practical situation. Now the most significant weight is added on the left-hand side of the scale. It can be seen that the readout of the scale is negative, so the heaviest weight is removed. Now the second heaviest weight is added to the scale. The readout is positive, showing that more weight must be added. So the next heaviest weight is added to the scale. The readout is still positive, so again more weight must be added. You probably noticed by now that the readout is checked each time a weight is added. If the readout is negative, the previously added weight is removed. These steps are repeated for the remaining weights. The digital code found is 01111. This code can be translated into its decimal representation, the procedure for which is shown. You will note that the found value is slightly lower than the unknown weight that was added to the right-hand side of the scale. This is implicit in the name of the algorithm, the successive approximation algorithm.
Now that we've seen the SAR algorithm in action in the scale analogy, we are ready to discuss a circuit implementation of the SAR ADC. Here we see a one-way example implementation. Closing and opening the upper left switch is the circuit equivalent of placing the unknown weight on the right-hand side of the scale. Voltage replaces the readout of the scale as our measured quantity. Toggling the middle switch is the circuit equivalent of placing a counterweight on the left-hand side of the scale. The new block, called the comparator, which compares its inputs, is used to check whether the balance is positive or negative. The minimal SAR ADCU circuit previously only contained an equivalent of one weight. Here, a 5-bit implementation using 5 capacitors is shown, with their weights demarcated. We will now walk through a conversion using the 5-bit circuit SAR ADC. The circuit is shown on the left. The graph on the right shows the balance voltage. The bottom digits make up the binary word representing the state of the capacitor switches. As before, we place our input by closing the upper leftmost switch. We start by testing the largest capacitor, which is found to produce a negative balance voltage. The capacitor is thus switched back to its original state, 0. Next, the second largest capacitor is toggled. The algorithm is carried out as shown in the scale analogy. The comparator helps us check whether the balance voltage is positive or negative, and thus whether or not previously added capacitors should be switched back out, or if additional capacitors need to be switched in. Now that the circuit has been explained, we will show a practical example. The SAR ADC is relatively power efficient when compared to other types of ADCs. As such, it is suitable for battery applications where direct charging access is difficult or inconvenient. Imagine an elderly man. He visits the doctor every day for his heart checkup. This is very taxing for the man. The man would much rather have a leisurely stroll in the park. Upon hearing this, the doctor gives the man an internet-connected portable SAR ADC-based heart monitor. With this technology, the elderly man can take a leisurely stroll in the park instead of visiting the doctor, while the doctor can constantly and efficiently check up on the elderly man.
We now hope that you know why we need ADCs, and of course, we now also hope that you have a little bit of an idea of how computers think and count.
Yes. We also hope that you intuitively understand how the successive approximation register algorithm works, how this can be used to make an ADC, and where this ADC might be useful in practice.